So now we are going to apply the changes into modifications into this equation. So by applying equation 2, 5 and 6 into equation 1, we get dg is equal to minus sdt, because this term dg by dt at constant pressure in Ni is equal to minus s, this dt. So we get minus sdt plus, look at this term, dou g by dou p at constant temperature and Ni. Dou g by dou p at constant temperature and Ni is v. Then we have this d theta is equal to v dp plus, we know Ga bar is equal to, G1 bar is equal to mu 1, right? So we can here, instead of G1 bar, we can write mu 1, then this dn1 plus mu 2 dn2. This is our equation 7. So we substituted all these terms into equation 1 and we got minus sdt plus bdp plus mu 1 dn1 plus mu 2 dn2. That is equation 7. Now we are going to apply conditions of constant temperature and pressure. Constant temperature and pressure, dt will be equal to 0 and dp will be equal to 0. So equation 7 reduces to dg will be equal to constant temperature and pressure will be equal to, so can we write these two terms cancels, right? Then we have only mu1 dn1 this term plus mu2 dn2. This is equation 8. So we have dg is equal to mu1 dn1 plus mu2 dn2. This equation 8 can be integrated for a constant composition system. If we are going to integrate for a constant composition system, we are not applying limits. Then we get g is equal to n1 mu1 plus n2 mu2. G is equal to n1 mu1 plus n2 mu2. Equation 9. Okay. So now we are with equation 9, that is G is equal to n1 mu1 plus n2 mu2. This is equation 9. Now we are going to imagine that the temperature and pressure are not constants. That is, temperature and pressure are changed along with the composition or amounts of components of the system. So we are varying temperature and pressure as well. In such cases, the total change in free energy can be given by the differential of equation 9. Okay, so when temperature and pressure are also varying, the total free energy change can be given as a differential of this equation 9. Let us see how it can be done. So we can write dg is equal to mu1 dn1 plus, second term. We are going to differentiate this term. So mu1 dn1 plus, now n1 as constant, n1 d mu1. So differential of first term. Now we have to find the differential derivative of second term. So it is mu2 dn2 plus n2 d mu2. Okay, so I hope it is clear. We just differentiated both these terms by applying product rule. Okay. Therefore, we can write dg is equal to, we are just going to rearrange these terms. Okay, so we get mu1 dn1 plus, take this term here, just rearranging mu2 dn2 plus n1 d mu1 plus n2 d mu2. This is equation 10. We just differentiate equation 9 and then rearrange terms. Now, the effects of changes in temperature and pressure are accounted by the terms d mu1 and d mu2. Therefore, we can equate equation 7 and equation 10. Okay, so equation 7 and equation 10 represent same type of change in free energy. So we can equate both equation 7 and equation 10. So we can write equation 1 was minus SDT plus VDP plus mu1 dn1 plus mu2 dn2, right? We can write it by summation. I is equal to 1 to 2 because it is a bicomponent system. So we can write mu I dni. So equation 7 was like minus SDT plus VDP plus mu1 dn1 plus mu2 dn2. We just wrote both those terms like this, which is equal to, this can be written as sigma I equal to 1 to 2 mu I dni, right? So sigma I equal to 1 to 2 mu I dni plus sum of these two terms. How can we write sigma I equal to 1 to 2 ni d mu I, ni d mu I. Okay, or we have similar terms, right? So look here, we have sigma I equal to 1 to 2 mu I dni. So we have the same term here, so we can cut them, and the remaining terms we can write sigma SDT plus VDP minus, let us take this term to left side. So minus sigma I equal to 1 to 2 ni d mu I plus ni d mu I, which is equal to 0. This is equation 11. So we have minus SDT plus VDP minus sigma I equal to 1 to 2 ni d mu I is equal to 0. Okay, so this equation 11 is the Gibbs-Duhem equation. This equation is the Gibbs-Duhem equation. From equation 11, it is quite clear that the intensive variables temperature, pressure, mu1 and mu2 are not independent. Okay, so temperature, pressure, mu1 and mu2, they are not independent. This fact can be expressed by saying that there exists a relation connecting the intensive variables, and this relation can be written as a function of temperature, pressure, mu1, mu2. So these terms, when connected, it can be expressed as 0. Okay. So this is the Gibbs-Duhem, not Gibbs-Helmholtz, sorry, Gibbs-Duhem equation. And the relation can be expressed as the energy is a function of temperature, pressure, mu1, mu2, etc. is equal to 0. Now for an isothermal system, isothermal and isobaric process, that means dt is equal to 0, dp is equal to 0, right? So equation 11 reduces to, for a binary system we can write n1 d mu1 plus n2 d mu2 is equal to 0. Okay, because this term is 0, this term is 0, what remaining is this term sigma na d mu I. We have splitted it for a binary system, n1 d mu1 plus n2 d mu2 is equal to 0. For a system containing I components, how can we write n1 d mu1 plus n2 d mu2 plus etc. plus ni d mu I is equal to 0. Or in another terms we can write sigma ni d mu I is equal to 0. Sigma ni d mu I is equal to 0 for an isothermal and isobaric process. Okay, equation 12. This is also known as Gibbs-Helmholtz equation. This is another expression for Gibbs-Helmholtz equation when temperature and pressure are kept constant. The significance of Gibbs-Duhem equation is that the chemical potential of one component of a mixture cannot change independently of the chemical potential of the other component, because the chemical potential of all the components in the system or in the mixture are interrelated. They are interrelated. So chemical potential of one component cannot change without changing chemical potential of other components. Okay. So for a two component system, we know N1 d mu 1, sorry, N1 d mu 1 plus N2 d mu 2 is equal to 0. From this we can take only d mu 1 on left side. So we get d mu 1 is equal to, this term is taken to the right side. So negative sign will be there. N2 d mu 2 divided by N1, right? Divided by N1. So we get d mu 1 is equal to minus N2 by N1 d mu 2. Let this be equation 13. By looking at the above equation, this equation 13, we can say that the variation in chemical potential of one component of the system can bring the variation in chemical potential of second component of the system. Okay, so when one component, chemical potential of one component of the mixture is changed, the chemical potential of other component also changes. So we have derived Gibbs-Duhem equation, and we have seen two different expressions of Gibbs-Duhem equation, and also we have proved that the potential of one component of the system, if it changes, the chemical potential of other components in the mixture will also vary. Okay.